Welcome, my friends! In this video, we will discuss tree diagrams. As you dig deeper into the world of probability, you will start to realize that due to the complexity of the world that we live in and the infinite possibilities of questions that can be asked, it is handy to have a variety of different tools ready to approach any given probability question. One such tool that can be extremely useful for visualizing and solving probability problems is what is called a tree diagram. A tree diagram is a visual display of all of the outcomes in any given statistical experiment. Let's start off with a simple example: the outcomes and probabilities associated with flipping a fair coin twice. This is how it works. I typically start at the left-hand side of my page and begin with a dot. From this dot, we draw branches. Each branch represents a possible outcome for the first event. In this case, the first event is the first flip of the coin, to which there can be two outcomes, either heads or tails. One branch will represent H, or heads, and the other will be T, or tails. We make two more dots at the end of the branches we just drew, and can continue with additional branches for the second event, flipping the coin a second time. We can have heads or tails, just like on the first flip. Since we are only interested in the outcomes related to flipping a coin twice, this is the end of the tree diagram. At the end of the last branch, we will write the outcomes. This path represents flipping heads twice, so we label it as HH. This path represents flipping heads and then tails, so we label it HT. Then we have TH and TT. We also write the probability of each event on the branches. There is a 50% chance of flipping heads and a 50% chance of flipping tails for the first flip, so we label each of these branches with a 0.5. Note that all of the branches coming from one dot must have probabilities that add up to 1. We also have 0.5 on all of the other branches, since every flip has a 50-50 chance of being heads or tails. Now, to find the probability of any of the four outcomes, we simply multiply the probabilities on the branches. For heads, we have 0.5 times 0.5, which is 0.25. Heads-tails is also 0.5 times 0.5. Well, it turns out that they're all 0.5 times 0.5 in our example, since every branch has a probability of 0.5. From this table that I made using the tree diagram, we can answer probability questions, such as what is the probability of flipping at least one heads? Well, we find all of the outcomes where there is one or two heads and add up their probabilities. The outcomes with at least one heads include HH, HT, and TH. The corresponding probabilities are 0.25, 0.25, and 0.25. Adding these probabilities together gives us 0.75. Let's look at a slightly more complicated tree diagram. Suppose there are 6 balls in a bag, identical except for color. 3 are blue, 2 are green, and 1 is red. You are going to draw 2 balls without replacing the first ball before selecting the second ball. Let's draw the tree diagram for this situation. We start with a dot. For the first ball, you can draw either a blue, a green, or a red ball, so we will have 3 branches from the starting dot. For the second ball, if you drew a blue ball first, then you can still draw a blue, green, or red ball. If you drew a green ball first, you also can still draw either a blue, green, or red ball. But if you drew a red ball first, there's only one red ball in the bag, so you won't have any more red balls left. You can only draw a blue or green ball at that point. We can see that there are 8 different outcomes. Follow the branches to determine what those outcomes are. We have blue blue, blue green, blue red, green blue, green green, green red, red blue, and red green. Now let's determine the probabilities on the branches. We are assuming that each of the 6 balls has an equal chance of being chosen from the bag. On the first draw, there are 3 blues, 2 greens, and 1 red. So there is a 3 out of 6 chance of drawing a blue, a 2 out of 6 chance of drawing a green, and a 1 out of 6 chance of drawing a red. You could reduce these fractions, but I would recommend that you don't, because having a denominator of 6 helps remind us that there are 6 balls in the bag. Also remember that all probabilities from one dot must add up to 1, which they do here. 3 out of 6 plus 2 out of 6 plus 1 out of 6 is 1. The second draw requires that you think a little bit harder. If a blue ball was selected on draw 1, then the bag now looks like this, with 2 blues left, 2 greens left, and 1 red left. Now there are only 5 balls in the bag, so the probabilities are 2/5 for blue, 2/5 for green, and 1/5 for red. If a green ball was drawn first, then the bag looks like this. 3 out of 5 are blue, 1 out of 5 are green, and 1 out of 5 are red. If a red ball was drawn first, we just have 3 blues left and 2 greens. So there's a 3 out of 5 chance of drawing a blue, and a 2 out of 5 chance of drawing a green. And we have no branch for red since there are no reds left. Okay, now we are ready for the probabilities. Just follow the branches. Blue is 3/6 times 2/5, which is equal to 6 out of 30. Blue-green is 3/6 times 2/5, which is 6 out of 30 again. Blue-red is 3/6 times 1/5, which is 3 out of 30. You could reduce these fractions, but again, I typically don't recommend it for these types of problems. As you will see, not reducing leaves everything with a denominator of 30, making adding outcomes together easier later. Alright, I'm going to give you a minute to pause the video and see if you can come up with the 5 remaining probabilities. Okay, we are back with the last 5 probabilities. Simply grab the probabilities from the branches and multiply them together. Also note that all of these numbers should add up to 1. I'll let you verify that one on your own. In case you didn't realize it already, the probabilities at the end of our tree are the joint probabilities. So the probability of blue on the first and blue on the second, the probability of blue on the first, green on the second, etc. The probabilities on the first branch are just the general probabilities, the probability of blue, probability of green, probability of red from the original bag. The second branch represents conditional probabilities, the probability of blue given blue was already drawn, the probability of green given a blue was already drawn, etc. Okay, once you have completed the tree, you can answer a number of different probability questions, which we will do with this table that I created. For example, what is the probability of drawing 2 blues? Well, that's just this outcome here. The probability of drawing 2 blues is 6 out of 30. What is the probability of drawing no greens? Just add up all the probabilities without greens and we will have the answer. The outcomes without any greens are these 3. Adding up the probabilities, we have 6 out of 30 plus 3 out of 30 plus 3 out of 30, which equals 12 out of 30. What about the probability of at least 1 red? At least 1 red would be either 1 or 2 reds, which are these outcomes. 3 out of 30 plus 2 out of 30 plus 3 out of 30 plus 2 out of 30 is equal to 10 out of 30. Okay, that completes our example. There are many circumstances when tree diagrams are useful and can help you visualize and calculate probabilities that would be difficult otherwise. The shortfall is that with too many events or outcomes, tree diagrams can get messy and difficult to create. Alright, that completes my video on tree diagrams. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.